So, on February 24th, 2026, inside an 8-meter-long vacuum chamber at NASA's Jet Propulsion Laboratory in Pasadena, California, an engine lit up that does not burn fuel. It does not use combustion. It does not use fire. It does not work the way any rocket engine has worked since the very first rocket left the ground nearly a century ago. What it uses is electricity, a magnetic field, and a metal called lithium turned into superheated plasma, accelerated by electromagnetic force to speeds that no chemical reaction can match. The tungsten electrode at the center of this engine reached temperatures exceeding 2,800 degrees Celsius during the test. That is hotter than molten lava, hotter than the melting point of steel, hotter than the surface of some stars. And the engine held 5 separate ignitions, 120 kilowatts of power, and not a single molecule of fuel burned. This is not an upgrade to existing engines. It is not a faster version of what we already have. It is not a bigger rocket or a better fuel mixture or a more efficient nozzle. It is a completely different way of moving through space. And the people who understand what that means are not using cautious language. NASA's own administrator said it plainly. This marks the first time in the United States that an electric propulsion system has operated at power levels this high, 25 times more powerful than the most powerful electric thrusters currently flying on any NASA spacecraft in existence. And the engineers who built it are not calling it a science experiment. They are calling it the beginning of the engine that will carry human beings to Mars. It is called a magnetoplasmadynamic thruster. And here is the part that should make you angry. This technology has existed on paper since the 1960s. The physics were understood. The math was solved. The concept was proven in small-scale laboratory tests, decades before most of us were born. And for 60 years, nobody built one that actually worked at the power levels needed for real missions. 60 years. We put humans on the moon with less development time than that. We built the International Space Station in less time than that. We invented the internet, mapped the human genome, and landed robots on Mars in less time than that. And the engine that could shorten a Mars trip from 9 months to weeks. The engine that uses 90% less fuel. The engine that does not rely on fire or combustion or any chemical reaction whatsoever, sat in filing cabinets and academic journals and university laboratories while we kept strapping ourselves to controlled explosions and calling it progress. And it is not just what this engine can do that matters. It is what it makes possible that was previously impossible. Because the reason we have not sent humans to Mars is not courage. It is not willpower. It is not national ambition. It is propulsion. Chemical rockets are too slow, too fuel-heavy, and too dangerous for a crew to survive a round trip to the red planet and come home alive. This engine changes that equation. Not by a percentage, not by an increment. It changes it fundamentally. Stay with me, because by the time this is over, you will understand why everything you thought you knew about how we travel through space is about to become obsolete, and why the most important moment in the history of space propulsion did not happen at a launch pad, with cameras rolling and a countdown clock on screen. It happened in a vacuum chamber in Pasadena, at 2,800 degrees, on a Tuesday in February, and almost nobody noticed. I am Graham Prescott, and if stories like this are what you come here for, subscribe right now because we are just getting started. What comes next in this story changes how you think about Mars, about the moon, and about what it actually means to become a spacefaring species. Let me start with something most people do not think about. Every rocket engine that has ever launched a human being into space, from Yuri Gagarin to the most recent Artemis mission, works on exactly the same principle. You take fuel, you set it on fire. The expanding gas pushes out the back of the engine. Newton's third law pushes the rocket forward. That is it. That is the entire mechanism. Fire. The Saturn V rocket that carried astronauts to the moon in 1969 was 85% fuel by weight. 85%. The rocket itself, the capsule, the crew, the scientific equipment, the lunar module, all of that fit inside the remaining 15%. The other 85% was just stuff to burn. The Space Launch System, NASA's current heavy-lift rocket, works the same way. SpaceX's Starship works the same way. Blue Origin's New Glenn works the same way. Better materials, better manufacturing, better computers running the flight software. But the same fundamental principle that a 14th century Chinese engineer would recognize if you showed it to them. Set something on fire. Ride the exhaust. For 80 years, we have been building more and more sophisticated versions of the same campfire. And the campfire has a ceiling. There is a physics limit to how much energy you can extract from a chemical reaction, and we are approaching it. Every improvement from this point forward is incremental. A few percent here, a few percent there, shaving weight, optimizing nozzle geometry, recovering boosters for reuse. All of it valuable, all of it real, and all of it working within a fundamental constraint that cannot be engineered around, because the constraint is chemistry itself. So the question is not whether we needed something better. The question is why it took this long. Because the answer to that question is more frustrating than you think. Let me explain exactly what happened on February 24th. Because the engineering matters. And once you understand how this engine works, you will understand why it is not an improvement to rockets. It is a replacement for them. The test took place inside JPL's COMET facility. That stands for Condensable Metal Propellant Vacuum Facility. It is an 8-meter-long, water-cooled vacuum chamber, specifically designed to safely test engines that use metal vapor as propellant. NASA calls it a unique national asset, and it is the only facility of its kind in the country that is designed for power levels reaching into the megawatt range. Inside that chamber, the team fired a prototype magnetoplasmadynamic thruster, an MPD thruster. And to understand why this matters, you need to understand the 5 steps of how it works, because every one of those steps is different from what a chemical rocket does. Step 1. Lithium metal, the lightest solid element on the periodic table, is heated until it vaporizes into a gas. Step 2. That gas is ionized by running an enormous electrical current through it. This strips electrons from the lithium atoms, turning the gas into plasma, the 4th state of matter, not solid, not liquid, not gas, plasma, the same state of matter that makes up the sun. Step 3. That plasma now sits between 2 electrodes carrying very high electrical current. The current flowing through the plasma creates a magnetic field. Step 4. The interaction between the electrical current and the magnetic field generates something called the Lorentz force. This is the same force that makes electric motors spin, the same force that powers maglev trains, the same fundamental physics that allows MRI machines to image the inside of your body. It is not exotic. It is not theoretical. It is one of the best understood forces in physics. Step 5. The Lorentz force accelerates the plasma out the back of the engine at extreme velocity. No combustion, no fire, no chemical reaction of any kind. Just electricity, magnets, and a metal turned into the 4th state of matter, and pushed by a force that has been understood since the 19th century. Think of it like a railgun, except instead of launching a solid projectile once, it launches a continuous stream of superheated plasma, and instead of firing for a fraction of a second, it fires for months or years. During the February test, the team achieved power levels of 120 kilowatts. To put that in context, NASA's Psyche spacecraft, which is currently flying through the asteroid belt, carries the most powerful electric thrusters on any NASA mission in history. Those thrusters produce a gentle, continuous push that accelerates Psyche to 124,000 miles per hour over time. The MPD thruster that was just tested in Pasadena is 25 times more powerful than those thrusters. 25 times. And why lithium? Because lithium has the lowest atomic mass of any metal. Lower mass means the electromagnetic force can accelerate it to higher velocities. Higher velocities mean more thrust per unit of propellant. It is the ideal fuel for an engine that does not burn anything. The tungsten electrode at the center of the thruster, the component that carries the enormous electrical current, reached 2,800 degrees Celsius during the test. Most metals on Earth would have liquefied. Tungsten held. It glowed white-hot in the vacuum chamber, plasma streaming past it, and it held. 5 ignitions, not a single structural failure. And here is the number that changes the entire calculus of spaceflight. Electric propulsion uses up to 90% less propellant than chemical rockets. 90%. Remember, the Saturn V was 85% fuel. Imagine a vehicle where that 85% drops to 8%. The mass you save does not disappear. It becomes payload. It becomes crew quarters. It becomes radiation shielding. It becomes food and water and breathable air for a journey that suddenly becomes survivable. So this engine does not burn anything. It turns metal into plasma and accelerates it with magnets. It uses 90% less fuel than a chemical rocket. It reached power levels that no electric propulsion system in the United States has ever achieved. And the team who built it did it in roughly 2.5 years with a partnership between JPL, Princeton University, and NASA's Glenn Research Center. But here is the part of this that should genuinely upset you. Now, let me explain why this is different. Fundamentally, categorically different from every previous propulsion improvement in the history of spaceflight. Every advancement in rocket technology over the past 80 years has been an upgrade to the same underlying mechanism. Better fuels, better nozzles, better turbopumps, better cooling systems, better manufacturing, including three-dimensional printing of engine components, reusable boosters. All of these are real achievements. All of them matter, but all of them exist within the same category. They are all improvements to combustion. They are all variations on the theme of setting something on fire and riding the exhaust. The MPD thruster does not improve combustion. It eliminates it. It replaces the entire mechanism of thrust generation with something fundamentally different. The difference is not between a slow car and a fast car. The difference is between a horse and a car. One is an improvement within a category. The other is a new category entirely. And this distinction matters for one very specific reason. Chemical propulsion has a ceiling. There is a maximum amount of energy you can extract from any chemical reaction, and the best rocket engines in the world are already approaching it. Electromagnetic propulsion does not have that ceiling. At least we have not found one yet. The theoretical limits of how fast you can accelerate plasma with electromagnetic force are so far beyond what chemical reactions can achieve that the comparison almost does not make sense. It is like comparing the top speed of a horse to the top speed of a jet aircraft. They are not even playing the same game. Either we keep refining controlled explosions, which have a physics ceiling we are approaching rapidly, or we switch to a fundamentally different mechanism that has no ceiling we can see yet. Those are the two options. There is no third. And here is the paradox that should keep every space policymaker awake at night. Because this engine, this thruster that just broke every electric propulsion power record in the country, is not new. It is not a recent invention. It is not the product of some sudden breakthrough that was unavailable before. The physics behind this engine were understood in the 1960s, 60 years ago. The concept was proven in small laboratory tests before humans had even walked on the moon. Research papers were written. Simulations were run. The math was clear. It worked. On paper, in small-scale experiments, in the theoretical framework of plasma physics, the MPD thruster was a solved problem more than half a century ago. Since the 1960s, the math was done, the physics were proven, and for 60 years, the filing cabinet won. Why? The answer is not conspiracy. It is not incompetence. It is something more mundane and, in some ways, more frustrating. Institutional momentum. Budget cycles, the gravitational pull of existing programs. When you have a workforce of tens of thousands of people trained to build chemical rockets, when you have supply chains optimized for chemical propellants, when you have launch pads designed for chemical engines, and when the missions on the schedule can technically be accomplished with chemical propulsion, however inefficiently, the pressure to keep doing what you are already doing is enormous. And that pressure won, because chemical rockets were good enough for what we were doing. Low Earth orbit, the moon, robotic probes to the outer planets. For those missions, the campfire worked. It was expensive, it was inefficient, it required enormous vehicles that were mostly fuel, but it worked. And when something works, even when something better exists, institutions tend to keep doing what works, rather than investing in what could replace it. Apollo consumed all the funding. Then the space shuttle consumed all the funding. Then the International Space Station consumed all the funding. Then the Space Launch System consumed all the funding. And the electromagnetic engine that could have opened the solar system sat in academic journals and conference proceedings, demonstrated at tiny scales in university laboratories, waiting for someone to fund the engineering that would take it from concept to hardware. The irony is sharp enough to cut. We spent 60 years perfecting the combustion engine of space, while the electromagnetic engine of space waited patiently in filing cabinets for the rest of engineering to catch up. And in one sense, that wait may have actually mattered. The material science that makes a tungsten electrode survive at 2,800 degrees did not exist in the 1960s. The computational modeling that lets engineers simulate plasma dynamics inside a thruster channel was impossible before modern supercomputers. The three-dimensional printing techniques that allow rapid prototyping of complex engine geometries are a product of the last decade. The 2026 MPD thruster is better than anything the 1960s could have produced, precisely because it waited. The technology waited for the rest of engineering to catch up. But that does not make 60 years of waiting any less maddening. But here's the part of this story that nobody is talking about. Because the MPD thruster is not the only engine NASA tested. There is a second one. And the second one does not replace chemical rockets for deep space travel. It replaces how chemical rockets burn fuel in the first place. At NASA's Marshall Space Flight Center in Huntsville, Alabama, engineers have been testing something called a rotating detonation rocket engine, an RDRE. And if the MPD thruster represents the future of interplanetary travel, the RDRE represents the future of getting off the ground. To understand why this matters, you need to understand the difference between two words that sound similar but mean something completely different in physics: deflagration and detonation. Deflagration is what every rocket engine you have ever seen does. Fuel and oxidizer mix in a combustion chamber. They ignite. The flame front moves through the mixture at subsonic speed. Controlled burning. Steady, manageable, predictable. This is how the space shuttle's main engines worked. This is how the Falcon 9 works. This is how every kitchen stove in the world works. Fuel meets flame. Combustion happens. Heat expands gas. Detonation is different. In detonation, the combustion front moves at supersonic speed. It does not burn through the fuel. It explodes through it. The energy release is faster, the pressures are higher, and the thermodynamic efficiency is fundamentally better. The RDRE figures out how to harness that. Instead of a steady, controlled burn, a supersonic detonation wave travels in a continuous circle inside an annular combustion chamber, detonating fresh fuel as it goes, around and around, thousands of times per second. Continuous controlled detonation. The difference between a campfire and a stick of dynamite. A campfire burns slowly and steadily. Dynamite releases its energy in a shock wave. The RDRE figured out how to make the dynamite continuous, and the result is an engine that produces more thrust per unit of fuel than any conventional rocket engine can achieve, because the thermodynamic cycle is inherently more efficient. Think about what that means in practical terms. Every rocket engine you have ever watched launch, from the Saturn V to the Falcon 9 to the Space Launch System, works the same way your kitchen stove works. Fuel meets an ignition source. A flame front moves through the mixture. Heat expands gas. The gas goes out the nozzle. Thrust. That is deflagration. The RDRE replaces that entire process with something closer to how the engine in your car works, except instead of pistons and cylinders and a crankshaft, it uses a continuous ring of supersonic detonation waves racing around an annealer chamber at thousands of revolutions per second. The combustion does not burn forward. It circles, endlessly. And every lap of that detonation wave extracts more energy from the same amount of fuel than any conventional combustion process can. How much more efficient? In the most recent tests, a full-scale RDRE combustor at Marshall fired for 251 seconds, producing more than 5,800 pounds of thrust. That kind of sustained burn is what a lunar lander needs for touchdown, or what a transfer vehicle needs for a deep space trajectory burn. And in April 2026, Astrobotic tested their own RDRE design, called Chakram, at Marshall, achieving over 4,000 pounds of thrust for a record 300 seconds of continuous operation while reaching thermal steady state, meaning the engine was not overheating. It could, in principle, run indefinitely. The engine is three-dimensionally printed from a copper alloy that NASA developed called GR-COP42, specifically designed to withstand the extreme temperatures and pressures of continuous detonation. And the program is already working toward a 10,000-pound thrust-class version that would be fully reusable. Thomas Teasley, the engineer leading the RDRE test effort at Marshall, said it directly. The RDRE enables a huge leap in design efficiency. It demonstrates we are closer to making lightweight propulsion systems that will allow us to send more mass and payload further into deep space. So let me make sure you are tracking what just happened. In 2026 alone, NASA successfully tested two completely different engines that each break from the fundamental way we have moved through space since the beginning of the space age. One replaces combustion with electromagnetism for deep space travel. The other replaces steady burning with continuous detonation for launch and landing. And together, they represent something that has not happened in the history of spaceflight. A simultaneous revolution in both how we leave Earth and how we travel once we are in space. Two different engines, two different physics, one destination, Mars. Now let me explain why this is not abstract. Because the implications of these two engines ripple outward in ways that touch every part of human spaceflight. Start with Mars. The reason no space agency has attempted a crewed Mars mission is not ambition, it is math. A round trip using chemical propulsion takes roughly 18 months of transit time, 9 months each way. During those 9 months, the crew is exposed to continuous galactic cosmic radiation, the high-energy particles that stream through interstellar space and pass through every known shielding material. Beyond Earth's magnetic field, there is nothing to block them. Every month in transit is a measurable increase in lifetime cancer risk. Every month in transit is additional muscle atrophy, bone density loss, cardiovascular deconditioning, and psychological strain. Chemical rockets cannot solve this problem because they cannot go faster. They are already near their theoretical limit. The MPD thruster, paired with a nuclear power source, changes the transit time. Less time in space means less radiation exposure. Less radiation means lower cancer risk for the crew. Less time means less food, less water, less oxygen to carry. Every kilogram of propellant saved by the engine is a kilogram that can become radiation shielding, or backup life support, or return trip fuel. The 90% propellant savings is not an engineering statistic. It is a survival equation. And it tips in favor of the crew for the first time in the history of human spaceflight. Then widen the circle. If the MPD thruster makes Mars reachable, it makes the outer solar system explorable. Jupiter's moon Europa, which almost certainly has a liquid ocean beneath its ice shell, an ocean that contains more water than all the oceans on Earth combined, becomes a destination for robotic missions powered by nuclear electric propulsion. The travel time to Jupiter with chemical propulsion is measured in years. With continuous electromagnetic thrust powered by a nuclear reactor, that timeline compresses dramatically. Saturn's moon Enceladus, which is actively venting water vapor and organic molecules into space from hydrothermal vents on its ocean floor, becomes reachable within reasonable mission timelines. Enceladus is currently one of the best candidates for extraterrestrial life in our solar system, and the only reason we have not sent a dedicated mission there is the propulsion problem. The same propulsion problem that a plasma thruster operating at megawatt power levels would solve. The asteroid belt becomes accessible for resource surveys. The ice giants, Uranus and Neptune, which have each been visited exactly once in human history, by Voyager 2 in the 1980s, become targets for orbiter missions instead of one-time flybys. The entire solar system opens up, not because we suddenly became braver, but because the math finally works. Widen it again. The economics of space change. When your engine uses 90% less propellant, the cost of every mission drops. The size of the launch vehicle needed to carry fuel drops. The number of launches required to assemble a deep space vehicle in orbit drops. The entire cost architecture of human spaceflight shifts downward, not by increments, by multiples. And there is a defense dimension that is already in motion. DARPA, the Defense Advanced Research Projects Agency, is actively involved with RDRE development through partnerships with Venus Aerospace. The military applications of engines that are lighter, more powerful, and more fuel efficient than anything currently flying are obvious and are being pursued in parallel with the civilian programs. Since the 1960s, this was a dream. In 2026, it became an engineering problem. And engineering problems get solved. But I want to slow down here, because this is the part of the story where the numbers stop being abstract and start being about real human beings. Imagine you are an astronaut. You have trained for years. You have passed every physical and psychological evaluation. You have been selected for the first crewed Mars mission. And now you are sitting in a vehicle looking at the mission profile. With chemical propulsion, your profile says 9 months in transit. Each way, 18 months total in deep space. During those 18 months, galactic cosmic rays will be passing through your body at a rate that ground-based humans never experience. Your bones will lose density at roughly 1% per month. Your muscles will atrophy despite hours of daily exercise. Your eyesight may deteriorate due to intracranial pressure changes in microgravity. And when you get home, assuming everything goes perfectly, your lifetime cancer risk will have increased by a percentage that your flight surgeon will discuss with you privately before you sign the consent forms. That is the mission profile with chemical propulsion. That is the reality of the campfire. It gets you there, eventually. But it exposes you to conditions that no human body was designed to endure for that length of time. In an environment where the nearest hospital is between 50 and 250 million miles away, depending on where Mars is in its orbit. There is no abort option. There is no early return. Once you are on a 9-month trajectory, you are committed. You ride it out, or you do not. Now imagine the same mission profile with nuclear electric MPD propulsion. The transit time drops dramatically. Every week you shave off that transit is a measurable decrease in radiation dose. Every week is less bone loss, less muscle atrophy, less psychological strain of floating in a metal tube between two planets with nothing outside the windows but void. The 90% fuel savings means the mass budget opens up. That extra mass can become thicker shielding, better life support redundancy, more consumables, a wider margin between survival and catastrophe. NASA Administrator Jared Isaacman said it in a way that sounds like a press release, but is actually a specific engineering goal, with a budget line attached to it. The successful performance of our thruster in this test demonstrates real progress towards sending an American astronaut to set foot on the red planet. That is not a slogan. That is a target. And for the first time, the propulsion hardware to reach that target exists outside of a filing cabinet and inside a vacuum chamber that has already been fired 5 times. So here is where the story arrives at the present moment. Because this is not a discovery that was made and archived. This is a program with a timeline. The tests are funded. The facilities exist. The next steps are already on the calendar. The MPD thruster test in February achieved 120 kilowatts. The next milestone is 1 megawatt. That is roughly 8 times the power of the February test. The Comet facility at JPL was specifically designed to handle megawatt-class testing. The infrastructure is already built. The chamber is already there. It does not need to be invented. It needs to be used. For a crewed Mars mission, the spacecraft would need between 2 and 4 megawatts of continuous power for more than 2.5 years. That power would come from a nuclear reactor carried aboard the spacecraft, part of NASA's Space Nuclear Propulsion Program being coordinated at Marshall Space Flight Center. The reactor provides electricity. The electricity powers the thruster. The thruster accelerates lithium plasma. And the spacecraft accelerates, continuously, for years, building speed in the silence of space until it is moving faster than any chemical rocket could ever achieve. That reactor does not exist yet in flight-ready form, but the program to build it does. And the physics of nuclear reactors in space are well understood. We have flown nuclear power sources in space before, including the radioisotope thermoelectric generators that power the Mars rovers and the Voyager probes. What is different here is scale. A multi-megawatt reactor is a different engineering challenge than a small radioactive battery. But it is an engineering challenge, not a physics challenge. The physics are solved, the engineering is in progress, and the budget line exists. The RDRE program is on a parallel track. The 10,000-pound thrust-class engine is the next target. Venus Aerospace, Astrobotic, and NASA's own team at Marshall and Glenn are all working on scaling the technology. The path from laboratory demonstration to flight hardware is clear. It is not short, but it is clear. Since the 1960s, this was theory. In 2026, it became hardware. And hardware gets iterated. Hardware gets tested. Hardware gets scaled. Hardware gets flown. That is what happens next. But I want to end on something that goes beyond the engineering. Because this is not just about engines. For 80 years, leaving Earth has required an explosion. Every astronaut who has ever flown, from Gagarin to the crew of the International Space Station, sat on top of millions of pounds of propellant and rode a column of controlled fire into the sky. Every satellite in orbit got there by burning something. Every probe we have ever sent to another planet was pushed there by combustion. Fire. The same fundamental force our ancestors used to cook food and stay warm in caves. We refined it. We controlled it. We engineered it into something extraordinary. But at its core, every rocket launch in history has been a very sophisticated campfire. The MPD thruster is not a better campfire. It is a different kind of force entirely. It does not roar. It glows. It does not shake the ground. It pushes gently, continuously, for months or years, building speed in silence until the spacecraft is moving faster than anything a campfire could ever achieve. It is the difference between paddling a canoe and turning on a motor. One is effort, the other is engineering. Somewhere in the coming decades, a spacecraft will leave Earth orbit heading for Mars. It will not be riding a column of fire. It will be powered by a nuclear reactor feeding electricity into an electromagnetic thruster that accelerates lithium plasma with the Lorentz force. The crew inside will not feel the violent shaking of a chemical burn. They will feel almost nothing. A gentle, continuous push, barely perceptible. And that barely perceptible push will carry them across 50 million miles of empty space to the surface of another planet. That is the future that the MPD thruster makes possible. Not the violent, shaking, fire and fury departure that every astronaut in history has endured. Something quieter, something steadier, something that works not by fighting physics with brute force, but by working with physics at the most fundamental level, using the same electromagnetic principles that hold atoms together and make stars spin. The physics for this were understood in the 1960s. The math was solved before the first human being walked on the moon. The concept was proven in laboratories where graduate students ran experiments that confirmed what the equations predicted. And for 60 years, the engine that could carry us to Mars sat in filing cabinets and doctoral theses and conference proceedings while we kept building campfires. On February 24, 2026, inside an 8-meter-long vacuum chamber in Pasadena, California, at 2,800 degrees, the filing cabinet lost. The universe just got a whole lot smaller. If this kind of story is what you come here for, subscribe right now and turn on notifications, because next time we are covering the nuclear power source that will actually fuel this engine in space. And that story is even wilder than this one. Drop a comment with what surprised you most. Was it the 60 years of waiting, the 90% fuel savings, the fact that two revolutionary engines were tested in the same year? Because most people have no idea any of this happened, and that silence is part of the problem. And share this with someone who still thinks Mars is science fiction. Because after what happened on February 24th, 2026, it is not. Not anymore.